So, dear students, today we will start heat transfer, theories of heat transfer. So, this is your 20th class on transport phenomena. In this class, first I would like to introduce you what this heat transfer is. In order to have an understanding of this heat transfer and similar subjects related to this heat transfer, I am citing an example. Let us suppose this is a container in which there is water at a particular temperature, this is room temperature. Water at room temperature, let us suppose 30 degree centigrade. I am assuming as this temperature is a room temperature, and let us suppose I am putting a heated metallic rod in this water. This is the metallic rod. Heated up to a temperature of, let us suppose, 200 degree centigrade. Once you dip it in this water at 30 degree centigrade, we will find that because of the fact that this heated rod that has been heated up to a temperature of 200 degree centigrade, so it contains associated heat with this rod, and once it will be dipped in the water at a lesser temperature than 30 degrees centigrade, what will happen? Heat energy will start to dissipate from this heated rod, and that will be taken by the water which is relatively at a lower temperature. If anybody asks you that what should be the equilibrium temperature of this system after the attainment of equilibrium, means neither the heat is being transferred from the heating rod to the water or from the water to rod. That means for the entire system the temperature is uniform. So, in the answer to the question asked by you that what should be the equilibrium temperature, so this equilibrium temperature should be the 200 plus 30 degree centigrade divided by 2, that is equal to 115 degree centigrade. This is the thing which can be extracted from the fundamental law of thermodynamics, that once the equilibrium is attained, thermal equilibrium is attained, then that is the so called the zeroth law of thermodynamics, then the equilibrium temperature can be calculated in this manner. This is what is the subject matter of the thermodynamics, a subject which is similar in many respects with similar to that heat transfer. This is the thing which can be derived from your thermodynamic principles or thermodynamics. So, thermodynamics can tell you that what should be the equilibrium temperature of the system under consideration, but it cannot reveal any idea that what should be the temperature of this rod after some time, after it has been dipped in the water. That means thermodynamics cannot express the temperature of rod as a function of time. If anybody asks you that what should be this temperature after, let us suppose after 20 seconds, what should be the temperature of this rod, this cannot be calculated using the principle of thermodynamics. Rather, the heat transfer, this subject that you are going to study, that can easily give you an idea that after a certain time what should be the temperature of this metallic rod by equating the concept the heat lost equal to heat gain, that is the heat lost by the rod, that should be equated to heat gained by the water at 30 degree centigrade. By doing so, you can easily determine that what should be the temperature of the rod after 20 seconds. It can be determined. This is what is the fundamental difference between two synonymous subject, that is the heat transfer and thermodynamics. So, the definition of heat transfer is so, as a note, you can summarize the thermodynamics it can reveal about the equilibrium temperature, whereas the subject matter of heat transfer, it can reveal about the equilibrium temperature as well as temperature after a given length of time, So, how that if you are assumed as the temperature of the rod that is equal to a function of time, differentiating this equation with respect to t, that is dt upon dt, that should be equal to 0 for this condition, for the equilibrium condition. Once the dt by dt, when you calculate this dt by dt, we will obtain an expression again in terms of t. So, this temperature of rod that should be equal to function of t. So, equating this equal to 0, we will obtain the equilibrium temperature that can be attained after a certain time. By you putting that time in this expression, temperature of the rod as a function of time, you will get the equilibrium temperature. So, the heat transfer enables us to determine the equilibrium temperature as well as to determine the temperature of the rod at any instant of time. So, basically the definition of heat transfer is it predicts the energy transfer taking place between two material bodies as a result of existing temperature difference between them. Whereas thermodynamics predicts the equilibrium temperature. This is the way by the virtue of which you can compare and contrast two synonymous subjects, heat transfer and thermodynamics. Now, we will study what are the different modes of heat transfer. Different modes of heat transfer. modes of heat transfer. The first mode is the conduction mode. So, the modes of heat transfer is A, the conduction, B is the convection, when the presence of fluid is there, and number C, the radiation, that is the heat transfer in which there is no material medium is required. That means only vacuum needs to be present there for the execution of the radiation heat transfer. So, in the case of conduction, number A, in solids conduction takes place as a result of elastic impact, as a result of elastic impacts. Why I am saying that the elastic impact should be there? As you know, the principle of elastic impact is that once the elastic impact between two material bodies having two different velocities takes place, in that case there is a interchange of velocity. Interchange of velocity, that means the interchange in the kinetic energy. So, taking the reference of the internal energy of the system, which is a combination of the potential energy, the kinetic energy, the translational energy, rotational, vibrational, all sort of energy. So, once the kinetic energy value is changed, so corresponding change in the other fraction of energy will also be there. So, in this manner this conduction takes place as a result of the elastic impact. In the case of solids, in solids which are non-conducting in nature, which are non-conducting in nature, conduction takes place due to oscillation of atoms. As you know from the very fundamental principles of quantum mechanics, that every atom has a tendency to oscillate itself about the mean position of rest. It means when all the atoms and molecules of a material which is non-conductor of heat, every molecule has a tendency to oscillate about its mean position of rest. So, this molecule, let us suppose there are two molecules in the vicinity. So, this is the mean position of rest for first molecule, this is the mean position of rest for the second molecule. So, around this mean position of rest there are two virtual positions of the molecule. This is the two virtual position of this molecule. That means at an instant of time these two molecules are coming closer to each other, and by this mode the conduction takes place. So, the oscillation of atoms has a major role to play for the conduction of heat energy in the conductors, in the solids which are non-conducting in nature. And the last, in solids which are conducting, conduction takes place due to the movement of free electrons. Conduction takes place due to movement of free electrons or motion of free electrons. So, from phenomenological point of view, heat conduction represents the energy transmission within a continuous body various parts of which are at different temperature, So, by the virtue of the different temperature at different location, the conduction mode of heat transfer takes place due to the presence of temperature gradient in a continuous body. This is what is the phenomenological concept of the heat conduction. So, question is how this transfer of the conduction heat energy can be quantified. How this conductive heat transfer can be quantified? This is our next task or then the final task of this present class. Let us consider a three-dimensional body. Let us suppose this distance is delta x, this phase has a temperature T1, this phase has temperature T2. So, if delta x is the thickness of a wide plate, let us suppose this is A is the surface area of this plate, T1 and T2 are the surface temperatures in such a manner that T1 is not equal to T2, because if the equal temperatures are there will not be any temperature gradient, there will not be any temperature difference. Temperature gradient is nothing but the difference in temperature over a distance, that is delta x here. So, T1 minus T2 by delta x is what is known as temperature gradient here. So, T1 and T2 are the surface temperatures, but T1 is not equal to T2, and if the K is the thermal conductivity of the material from which this plate has been made, thermal conductivity, and let us suppose QH is the heat energy transferred per unit time, then the expression for QH is K into A divided by delta x into T1 minus T2 if T1 is greater than T2. So, this is the expression for the quantity of heat energy transferred through the conduction mode. This is called the Fourier law of heat conduction. Coming back to the second part, that is the convection. Convection mode of heat transfer. In this case, the bulk motion of fluid is responsible for this mode of heat transfer. For this mode of heat transfer, if QH is the heat energy transferred per unit time due to convection, time due to convection, then QH is equal to H into A into temperature of the surface minus temperature of the fluid. Sorry, temperature of the fluid minus temperature of the surface if Tf is greater than Ts. Let it be question number 1, let it be question number 2, where here it is necessary to understand this H is called the convective heat transfer coefficient. H is called convective heat transfer coefficient, which is nothing but it is replacing the thermal conductivity which is the principal term in the conduction heat transfer. That K has been replaced by the convective heat transfer coefficient if the convective mode of heat transfer is going on. So, this H is called the convective heat transfer coefficient, which depends upon this value of this convective heat transfer coefficient depends upon the factors are physical properties of fluid, such as the specific heat capacity, the enthalpy, all sorts of these things, the property, the density, the kinematic viscosity, all those things that comes on the physical properties of fluid. It also depends upon the geometry of the system, and the third thing on which the value of H depends is the temperature difference between surface and the fluid. These are the three factors on which the value of this convective heat transfer coefficient depends. The last mode of heat transfer is the radiation mode. Last mode of heat transfer is the radiation mode. Radiation mode of heat transfer. This mode of heat transfer is due to the propagation of electromagnetic waves, that is called in abbreviated form as EM waves. Since the propagation of electromagnetic waves does not require any material medium, so this mode of heat transfer also does not require any material medium to be there. Rather, the vacuum needs to be present for this type of heat transfer. The energy coming from the sun to the surface is an example of the radiation mode of heat transfer, where the heat energy is being dissipated through the vacuum. So, and that is due to the travelling of the electromagnetic waves through the vacuum. So, this mode of heat transfer is due to the propagation of electromagnetic waves. So, in this case, if QH is the heat energy transferred due to radiation per unit time, then the QH, that is equal to A into epsilon into sigma e raised to the power 4, where A is the surface area of the surface from where the heat energy is radiating, Epsilon is a quantity called emissivity, that is the quantity of heat energy transferred per unit area per unit time, that is called the emissivity. That will be dealt in detail in the next class, followed by this class. Epsilon is called the emissivity of the surface, Sigma here is called Stefan-Boltzmann constant. This is a constant which can be derived on the basis of the quantum mechanical principle and the principles of quantum statistics or statistical mechanics. So, this is called the Stefan-Boltzmann constant, and T is the temperature on the absolute scale, that is in the temperature measured in the Kelvin. So, this is all about the various modes of heat transfer which are there, and these are the mode of heat transfer which we will study in the coming classes. And in the next class I will start the radiation first. Radiation mode of heat transfer will be taken care of first. That means we will see there what is this emissivity, what is the emissive power, what is the Planck's law of radiation, what is the meaning of the monochromatic radiation, and why a monochromatic radiation is important to consider. And in the next class we will also see how this Stefan-Boltzmann law of radiation can be derived from the Planck's law of monochromatic radiation. Thank you for the present class.